Hello, welcome to Electronics Education. I'm Vincent Chang. Today I'm going to continue the lesson on the small signal model of the previous one is the MOSFET. But this one, we're going to switch to the bipolar junction transistor. But the parameter, the AC parameter, stays the same, which is the transconductance. So alternating current analysis, AC analysis and small signal basics, part 2. BJT transconductance. BJT transconductance. So in the previous lecture, you have learned the transconductance of MOSFET. So this one, we can go a little bit faster, okay? Okay, assuming you have digest the previous lesson. For active mode, assumption for transistor bias. And then, if you send in the AC input voltage VB, then the device will be multiplied. The VB will be multiplied by a quantity and send out to and show up at the output terminal becomes a current. So that quantity is called transconductance. So IC equals VB times the GM. Okay? IC equals VB times the GM. So for active mode, the exponential, ideally, if we neglect the base width modulation, exponential relationship between the IC output current and the input voltage, so it's the largest signal. Total instantaneous signal relationship, exponential. So it's the exponential IV curve. Exponential IV curve. IC versus VB, large signal, total instantaneous. So now, here's the DC operating point. Let's start with the DC operating point and then send in an AC input voltage. Superimpose an AC input voltage VB. As long as the VB is a small signal, then triangular waveform in, then it will almost exhibit no distortion, and coming out of the collector show up as a current, the IC. So VB and IC. And then as long as it's the small signal, but as I mentioned in the previous lecture, the small signal is not the absolute definition. It's the relative definition associated with what device you are referring to. For the MOS, it's a small signal. It's defined as a small signal. The one that defines a small signal in MOSFET, if you take that signal to the bipolar, it could become a large signal. All right? So look at this. The small signal's definition for the BJT is more strict. It's more strict in terms of the thermal voltage, not threshold voltage. At MOSFET, it's threshold voltage. No, sorry, excuse me. For the MOSFET, it's threshold voltage. If you go back to a previous lecture, the definition for the MOSFET's small signal is much less than 2 overdrive. The VGS minus threshold voltage. But here, it's much less than the thermal voltage, 25 millivolt. So 0.1 volt is too large. 0.1 volt is too big. 1 millivolt, 100 millivolt is too big. Must be much less than 25 millivolt. So usually it has to be 5 millivolt, yes. 2 millivolt, yes, it's a small signal. Under this small signal condition, then the exponential curve can be approximately treated as a straight line. And the slope of that straight line is defined as the transconductance. The slope of that straight line is defined as the transconductance, right? So the purple triangle manifests the beautiful relationship among these three. Two variable and one very important quantity called transconductance. Height, IC, divided by base, VB, equals the slope. Okay, so always remember this. So as for the formulation of the transconductance, you can be easily derived from the largest signal exponential relationship. So it's similar to what we did in the MOSFET. So it's the partial IC, partial what? VB at the operating point. Partial IC, partial VB at the operating point. So based on this, following this exponential IV curve, the exponential still remains as an exponential. And VT chain rule has to go to the front. So what did you see? Because the IS, this one is actually the DC bias current, right? It's the DC bias current. So this is a very common formula, very important formula you should somehow remember. The transconductance for the MOSFET is proportional to, if you remember, MOSFET. I'm talking about MOSFET. In the MOSFET, it's the square root of the bias current, right? But here, for the bipolar, it's linearly related. It's the linearly proportional to the bias current and divided by the thermal voltage. So if 1 milliamp bias current divided by 0.025 volt is 40 milliamp divided by volt. Milliamp divided by volt. Here's the takeaway. For the transconductance, first is the definition constraint of the small signal. So under this small signal approximation, then the exponential IV curve can be approximated as a straight line. And that slope tells us the transconductance, right? And this purple triangle is a beautiful description among the three. What three? IC. I just want to show you the slope of its GM. Okay? What three? The two variable and the one AC parameter. So IC divided by VB equals the GM. And then the GM, the second one, the GM is the AC parameter. This AC performance parameter is decided by two things. Number one, the DC bias current. Number two, temperature, right? Because the temperature will decide the thermal voltage. So in the next lecture video, I'm going to teach you something that's puzzling a lot of students. Some of the key concepts of the AC analysis, I believe it will lay you a good foundation before you go into the amplifier's small signal analysis. Thanks for watching.